spacecraft. The indentation marks are Vickers indentation hardness measurements that were made before in this specimen. We will see these as we go up in magnification. To give you an idea of the size of the specimen, I will put a marker for identification and measurement purposes. We have now in the field of view a metric scale. Each line is 1 millimeter in division. So we see that this specimen is 1, 2, 3, 4 millimeters across, and about the equivalent size in the other dimension. Let us go now to a higher magnification and observe what this specimen looks like. Using now a 4x objective giving around 50 some-odd diameters magnification, we can see the marks of the Vickers indentation, showing a typical example of a metal. These markings were made in Zurich, Switzerland, and you can see the swell marks of the material as it is being pushed out by the diamond indenter. The surface was not highly polished, so one has now the marking of the polishing equipment. There are still occlusions in the material. In the specimen I examined previously, one would get a combination of crystalline deposits and metals. This one now is more completely metal. This is the next stage after the previous one, number 6. One can see now a much more precise evidence of a metal. We'll rotate the Wallenstein prism to bring out again. Here are structures. These are structures now that would not be seen normally except with the skill of this type of development. These are areas of higher reflectivity. These are structures that are present here. One is seeing this by shifting a prism. I'm going to do it again. There it is. These bear investigation. There are things beyond that which are just looked at with ordinary light. Here we can see with the power of a television camera. This is the information that we should be looking at. Okay, we'll move on. This specimen was taken the first late summer last year, 1977 specimen of the metal from the Spacecraft. This apparently was the one that disintegrated, and now we'll look at it. This is polarized light at higher magnification. The exciting thing about this specimen is you can see the various discrete agglomerates of metal, two distinct states, one here and another one in the more uniform polished background. These materials yet are not fused together, and one can see them even more critically by rotating the Wallenstein prism. Here's the edge of the specimen where it is molded in. One sees two distinct materials. Now we will go to polarized light to see if these materials are birefringent. Now under polarized light, one sees the distinct birefringent bits of material that are present against a matrix which is non-birefringent. I'll remove the analyzer. One can see this, and when one brings the analyzer in, one can see this, and has the polars crossed, one gets a birefringent area. One can be totally misled if one did an analysis of this in a gross way. One has to analyze now each of these areas. We see here the distinct birefringent areas with the polars crossed. Now I'll pull the analyzer out. One can see them, but much more distinctly that there is a birefringent area. This is number 1 sample, and as we go from 1, 4, 5, and 6, one sees a progression of diffusion of this birefringent material into the non-birefringent area. We must now analyze this material in this number 1 sample and move in the step-by-step evolution of this material into the final form that they have. It is very interesting to follow this, and one has to work now at this microscopic level. We are here now at about 160 diameters. These particles are very small, and one must deal with this on a microscopic basis. This is the end of the section now on the metals and metal samples that were given to me for examination. I was going to share this results with one of the people from NASA Ames Research Center, a Dr. Richard F. Haynes. Mm-hmm. I put the specimen away in this plastic envelope, which I have here, and when I took the envelope out of my pocket and went to share it with him, the specimen was no longer present. It had disappeared. I retraced my steps, checked with Dr. Wee, my wife, everything. I had 2 of the specimens fitted together this way. There are 3 of them all together in my pocket. And at this time, I no longer had any additional this specimen.
Before we go to the another specimen, what is your opinion about the disappeared metal, or materials, whatever it is? Is it normal? Normally, is it exist well on the Earth, on our world, or?
I've had this happen before to me, and when I've worked with crystals like this,
yes,
I'd work with a crystal, study it, as I have over the last 10 years, and suddenly the next day I won't go to reach for it and it will be gone. It will have disappeared. Mm-hmm. I first accused myself of being negligent and not paying attention. And finally I just put it aside. I said, if it happens, it happens. I won't let it bother me. I don't know how to explain it. I have no way of giving any rational explanation. And at this moment I must categorize it as a mystery.
I see. And what is your result of the
of this here?
Of this material?
Right now,
yes,
I could not explain the type of material that I have and its discreteness by any known combination of materials. I could not put it together myself as a scientist. To get a combination of thorium, silver, and silicon in discrete areas. Yes, if I were to melt it together, I would see the evidence of all of it. But their discreteness is what intrigues me. Do you understand what I'm saying? Because you see, if I were to take these combinations and put it into a furnace, melt it, then pour it out and pull a little ingot, I would see all of these elements present there in any one area. But I don't. I see this discrete bits of material. Now, it can only happen